All right, so just to kind of practice a little bit of what we did yesterday, remember we said a differential equation is an equation that has the derivative in it, okay? So we have here the derivative, the second derivative of y minus y equals 0. And we want to see if these three functions that were given are solutions to this, okay? Now, one thing that sometimes is helpful is just to describe what's going on here. What does this say about the second derivative?
It equals the function.
Yeah, the second derivative equals the original function. Okay? So basically you take the derivative twice. If you end up with the same thing you started with, then it works for this differential equation. Okay? So, this is a little thin. Let's make it a little bigger. So let's start with sine. What's y prime?
Cosine.
Cosine. What's y double prime?
Negative sine.
Negative sine x. Does that equal y?
No.
No. So this is not a solution. Okay?
What? Wait, what are we required to do?
Yeah, what's the question?
The question is this a solution to this equation? All right?
Like the differential, the derivative of the y is equal to the original function?
Correct. Okay? That's what we're trying to see, and it did not work for sine. But let's look here at this one. Y prime would equal what in this case?
Or
4e to the
for
negative x.
e, then negative.
That's it.
No, we need to do chain rule.
Yes, we do need to do chain rule. So it's negative 4e to the negative x, right? Okay? So now if I take the derivative of that,
Then we go back.
negative 4e to the negative x times the negative 1 with the chain rule. Hey, that does equal y. So this function is a solution to that differential equation. Okay? Here's another one. What's y prime? If c is a constant, c e to the x. What's y double prime? C e to the x. So this isn't changing.
So that's the solution.
It's the same thing. That's the solution as well. Okay?
Yep.
So that is a little bit more working with differential equations. Here we're not solving, we're simply verifying that we have a solution. Okay? So then we had another case where we can verify a solution and then use that solution to find a particular solution. And this was the very end of what we did yesterday. So the first thing that we're doing here is we want to verify that c times x cubed is a solution to this equation xy prime minus 3y equals 0. Okay? So we have xy prime minus, well, y is a cx cubed. So I need to figure out what y prime is.
Yeah.
All right, what is y prime?
3cx to the square.
Yeah, 3cx squared. Okay? By the way, every one of you at some point is going to now start mixing up the antiderivative rules with the derivative rules. And all I can say is just be careful. Okay? You just kind of have to constantly keep the rules straight in your mind. All right? So, now I'm plugging this in. X times 3cx squared minus 3cx cubed. Okay? And actually I should have put a question mark here. Does this equal 0? And we find that yes, 3cx cubed minus 3cx cubed does equal 0. So we have verified this solution. Okay? I had a bad set of parentheses there. It should have been just here. Okay? So now they want the particular solution with the initial condition y equals 2 when x equals -3. The initial condition is simply a point that we're wanting this general solution. Remember, this with the constant in it is a general solution. The initial condition is a point we want that thing to hit. So, oh wait, sorry, I circled the wrong one. This is the general solution. We want it to hit the point -3, 2. So I'm going to be plugging in the 2 for y and c times -3 cubed. That's a -27, so c is -2/27. And that means the particular solution is y equals -2/27 times x cubed.
Yeah.
Okay? So, if you remember yesterday when we were looking at taking the antiderivative, you had the plus c's. That kind of gives us a family of functions. And then you have a particular point. Theoretically, on a family of functions, you could make it hit whatever point you wanted.
By changing the constant.
By changing the constant, yeah. So we plug that point in, figure out what the constant has to be to hit the point, and now we have our particular solution. Okay?
Yeah.
So, relatively simple concept, just got to plug it in, solve for c, and you've got it. So now we can look at slope fields. These are pretty cool. Once you figure out what in the world they are, they're pretty cool and they're pretty simple to work with. I'm going to turn the light off just so that we can see a little bit more closely here. This is a slope field. You can see all those little dashes around. Okay? And what you can find, what you can find with these slope fields is actually you can tell something about the original function, because this is telling us what's going on in the function as x and y change. Alright? So as I look at this one, I see, it may be a little hard to see because of the drawing, but I can see that all these places where x equals 0, my derivative equals 0. Okay? So these are just kind of notes that we would make mentally. If x equals 0, the derivative equals 0. Okay? What else do you notice as I look at a column of these? Does my y coordinate impact the slope?
No.
No. Alright, so that's another thing. As you look at a slope field like this, if I see no change in the slope as the y is changing, that means that y prime has no y in it, in the equation. Okay? You could have y prime equals 2x minus y or something like that, and you're going to see a change as you go up and down. Now, as you go side to side, notice it is changing, so that means we will have an x in this equation. But let's look at how it's changing now. We already said it's 0 when x is 0. Look at it when x is 1, and then when x is 2. Over here, x is -1. Here, x is -2. Okay? So as x increases, the slope is increasing. As x decreases, the slope is decreasing. Another thing you can do here is kind of try to approximate what this function is. Just looking at the curves here, what does it look like? Yeah, it looks like a parabola. Like if it were hitting this point, it looks something like this. This isn't the greatest sketch. Okay, it looks something like that. Now, we have these three equations on the bottom here. Y prime is x plus y. but hey, though it's not changing as y changes, so I know this one isn't it. And I also know this third one isn't it, because that has a y in the equation and it doesn't have an x. Okay? But if I look at y prime equals x, that is the differential equation for this slope field.
X squared is the parent function.
Yeah, and if you take the derivative of x squared, 2x, it's a linear, so it makes sense that our slope function is a linear function. Okay? Now, I know I skipped the drawing at the top. We're going to get back to that, but I found it's helpful to see this a little bit first.
Wait, can we draw this kind of graph by the calculator?
No.
So we have to draw it on our...
Yeah, your calculator doesn't do this. We'll look at how to sketch them in a sec here, though. Let's look at this one here. As I look across a row, is this one changing as I look across the row?
Yes.
Yes. So since there is change, as I go side to side, that means y prime has an x in it. As I look, it may be hard to tell in some of these, but as I look down a column, is it changing?
Yes.
Yes. So y prime has a y in it. Okay? Well, as I look at my two choices, there's only one that it could be then. It's this one. Okay? But there's one more thing we can actually look at, and this happens a lot. Look for the ones that are horizontal. Okay? It's horizontal here, 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 here.
Yeah.
And if I look at a particular point, okay, it's horizontal along that diagonal line. What's the equation of that line? If I were to connect all those. Y equals negative x. So the slope here is -1, right?
Yeah.
So y prime is going to equal 0 when y is the opposite of x.
And that's true for the first one.
And that's true if you look at this equation. If I had x plus a negative x, I'd get 0. Okay? So that's another thing you can look for as you're trying to see which differential equation goes with the slope field. Okay? Alright, one more here. Notice on this one, when y is 0, my slopes are all 0. As I look at a column, is y changing?
Yeah.
Yeah, so it has,
Y in it.
there is a change, so it has a y in it. Y prime has a y. Okay? As I go side to side, though,
It doesn't change.
Yeah.
no change. No change as we go side to side, so y prime
Doesn't have.
doesn't have an x. Alright, and that matches up with our final choice here, y prime equals y. Notice when y is 0, the slope is 0. And you can even see up here, y is 1, the slopes there look about to be 1.
Yeah.
Okay? Here where it's 2, it's even steeper, and so on. You can kind of confirm as you look through the rest of this. Okay? Alright, so that's what a slope field is, and that's how we can kind of look at it and tell what's going on with the differential equation and also with the original function. Okay? We could sketch some of these if we wanted here. But let's see how these slope fields actually are made. And it's actually a pretty simple process. First of all, we start with a differential equation. Okay? Here we have the differential equation y prime equals x minus y. If I want to sketch a slope field for these points, first of all, I plot the points. Okay? And then what I do is I figure out the slope for each of these. So y prime is x minus the y. Well, that means we have a slope of -2. So over here at this point, I need to kind of eyeball what a slope of -2 would look like. Well, -1 would be about down here, so I need to aim for that. You know, this would be down 2 over 1 if I aimed for there. So I'm going to put a slash like that, and then I can erase the extra little guidelines I put on there. And there's the slope of -2. Okay? At the point 0, 1. Okay? Y prime is literally 0 minus 1. X minus y. So that's -1. Okay, so if I aim over here, okay, there's my slope of -1. I'll erase the extra little guidelines I put on there, and there it is. And then for the last one, 1, 1.
Are you just good at the angles because you've been doing it, or like you know how to, like, I don't know how accurate I would be able to draw.
Well, I'm just using rise and run. Like on this, rise over run, I go down 1 over 1, so I need to aim for here. So then you're just kind of eyeballing it, you know, try to do a straight line. You can use a straight edge if you need. But again, these are kind of approximations of what it would be. So it's not necessarily going to be perfect, but and you'll see on the next one we do too, there's a little bit of eyeballing that goes on. So you just do your best and try to make it recognizable. Really, it's kind of consistency, as we'll see with the next one. If I had multiple points that all had a slope of -1, as long as those were all about the same, and they were less steep than the -2 ones were, you know, you'll be able to see what you need to see. Okay? And like here, where at the point 1, 1, it's 0. So we just put a little horizontal thing there. Okay?
But why we do that? Like, use. How could we do that?
Well, we were only told to find the slope field for these 3 points. Okay? We could be told to find the slope field for more points, and that's actually what this has. Okay? So here we have a whole bunch of points. We have -2, 1, -2, -1, and so on. Okay? So let me plot all the points here. Okay? So here are the points. And down at -1 as well. And we're given the differential equation y prime equals 2x plus y. And they're really nice to us. They already figured out what all the slopes would be, because we assume you can plug values in. Okay, so -2 times 2 is -4 minus the y minus the -1, or plus the y is -1. So we have a slope of -5 at the point -2, -1. So we come over here. And this is where kind of the eyeballing comes in. -5 is going to be really steep. So I'm just going to put it like that. Okay? And then I notice at the next 2 points, -2, +1, and -1, -1, the slope is -3. Okay? So, for those, I'm going to make it a little less steep than the -5 was. Okay, and I'm going to try to make those the same, the best I can. Alright, so then we have the points at -1, 1 and 0, -1, we have a slope of -1. This one I can get a little better idea of because -1 would take me like this. So it's going to hit that, and I'll just erase this extra. Same thing from -1, +1, I'd aim at the origin to be a slope of -1, so right there. And erase the extra. Eraser. Okay? Then, by the time I get to the next 2 points, I'm at a +1, so I'm doing the same thing. There's a +1, there's a +1. Again, try to make those about the same. And then at 1, 1 and 2, -1, I have a slope of 3. So +3 is going to be more steep, like that. and then the last point I have a slope of positive 5, so that's really steep. Okay? So there's our slope field for this situation. And now if I want to sketch the graph of y through this point 1, 1, well, here's the point I have, and I know the slope right at that point is there.
Yeah.
So now you gotta kind of use what you know to figure out, okay, where am I going to be changing? And that's where if you kind of look at these ones that are parallel, okay, I know that kind of halfway between those two, I'm probably going to have that slope. Okay, so there we have that. And then kind of halfway between these guys, I'm going to have this slope. Oop, let's fix that angle a little better. Okay. And then probably halfway between these guys, I'll have that slope. Now, you also kind of have to travel along the path that you're taking. So like I'm going down this way, I've got to kind of curve into this. To be going up somewhere in here, I've got to have a minimum, right?
Yeah.
And then to be going that steep, I'm going to go up this way. And by the time I get here, by the time I get kind of between those two, I've got a slope of positive 3. And by the time I get out here, I've got a slope of positive 5. Okay?
Yeah.
Or negative 5, I should say. I'm looking at it upside down. Okay? Alright, if I go over here to the right, by the time I continue to go out, at some point here I'll be at a slope of positive 5. Okay? But there we have a general sketch of about what this graph would look like. And I can get rid of these extra little marks that I used. And we'll have our slope field along with a sketch of a graph. And if you look over here, that's what it should look like. Okay? So our sketch was pretty close. Okay?
It's kind of cool.
Yeah. It's not, and that's the nice thing, it's not too hard. These are kind of fun to do, you know?